We'll begin with 6.2.3.2, the properties of the DTFT first, and then we'll go to the previous slide, which is the properties of the DTFS. Now, for the properties, basically, we assume that we are given xn and x omega, the DTFT of xn exists, yn and the y omega axis, and then let's see what happens when we are given xn and yn in time. So this is time versus what happened to x omega and y omega in frequency. So these are the most important properties we need to know. Linearity basically means that if we have the signal in time and we sum them up in the frequency, we also sum them up. Alright, then if you say where's the proof? Well, I put the proof somewhere here in the handout 2, 6.2, handout 2 DTFT properties. So we go to 6.2, handout 2. I've done some of the properties over here, 1, 2, and 3, only some of them, because as engineers, we are basically more interested to use the properties than to prove them, although we'll prove some of them. Alright, I'll highlight all those that are needed in our course. So we need at least these 5. First one is linearity. Time shifting basically means that we are going to delay our sequence. And in Z transform, you'll see that actually it is nothing but Z minus N naught. And in the DTFT is X omega, the original DTFT of Xn, and multiplied by E minus J omega N naught. So they are all very similar in their expression if you compare them closely. Frequency shifting is used very much in digital comms. Basically, in the frequency shifting, we are multiplying our original signal with a complex exponential. Actually, we are always multiplying with cosine or sine of a particular frequency. But when we multiply a particular frequency with the original sequence, in the frequency domain, we are translating x omega into to be centered at omega naught. That's what it means here. The last two that we need you to know is convolution in time. So this is called the convolution in time is multiplication in frequency. So in Laplace transform, in the Z transform, you have also seen that. As well as multiplication in time, when we multiply one sequence with another sequence, then this looks like convolution in the frequency. Now, this is the DTFT transform that we need you to know. And what about the DTFS? Well, the difference between the DTFT and DTFS is xn becomes not x omega, but actually becomes the coefficients of the DTFS. Typically in this book we put CK, but in some books they put AK. So here I took AKs and show you that it is AK. And to get the DTFS coefficients, it is what you have known so far, 1 over n over one single period xn times E minus J k omega naught n, where omega naught is of course 2 pi over n equals to omega naught. Right, so we have now defined what is AK, which is the DTFS coefficients of xn. So, and what about BK? BK is the DTFS coefficients of yn. And then again, we show you that when this is a periodic signal, okay, xn and yn are periodic, then the DTFS is also sum. The time shifting, where we delay the sequence by n naught, then the AKs, so xn is DTFS is AK. We do not need to recompute, we simply use this property, AK times E minus JK 2 pi over n times n naught. The coefficients is changed by that way. And if you look very hard, what is E minus J 2 pi over n times k times n naught? Is basically this is 1, the amplitude is 1, and this is the phase. theta. So in fact, all we're changing is not the magnitude of AK, but we're changing the phase of AK. So in many books, you would say a time delay results in some phase shift of the coefficients of the DTFS. That's what it's meaning. Alright, so we are also interested in the frequency shift. Basically means that we multiply a complex exponential with the original sequence, and here in the in the coefficients, then you realize that the coefficients are shifted along the frequency, and of course we are indexing at k. So we are multiplying by m times 2 pi over n, the frequency. We're shifting by m. Alright, and the last one is, the last two we really need you to know is periodic convolution. Remember, x and y are periodic, and when we convolve them, then there is something called periodic convolution that will come out. So you must be careful. Later on, you will see that we will examine this periodic convolution very carefully. And then what happens in the frequency domain is simply that we are multiplying again the coefficients AK and BK, but we need to introduce the n here. Lastly, when we multiply the two sequence, then in the frequency domain, we are actually convolving these two coefficients over here. So the thing to note is that you have to compare the DTFS coefficient properties versus the DTFT properties. You will see that most of them are the same except the convolution. Over here, this is the linear convolution, and this is the periodic convolution, and the most telltale sign is this guy, where we are actually using a repeating versions of y. Okay, as well as over here, we're repeating version of n, the period n here. With that, I think we are done with convolution of DTFS and DTFT. Thank you.